Okay, so let's hop over to OneNote and get started. So essentially the idea here is this is going to give us a way to reverse the chain rule from the derivative. And the best way to do this is just with a bunch of examples. So main idea is to, so the substitution rule gives us a way to reverse the chain rule. Right, essentially remember the chain rule. So let's recall that. The chain rule from differentiation said if you were going to differentiate f of g of x composed functions like this, what you would do is you do f prime of g of x times g prime of x. So we see one function plugged into another one. So let's see how this will look, how we'll do this. I'm not going to write down any formulas because it's more just understanding how to set it up and kind of be organized. We kind of just want to identify the composed functions and where the derivatives are going to come from. So example, let's say we want to compute the integral of 2x times the square root of 1 plus x squared. So you might notice that if you look at what's on the inside of the square root 1 plus x squared, notice that if you take the derivative of 1 plus x squared, that would be exactly 2x. So we can kind of see that that's where we'd like to make a substitution. So the way we do that is we say let u, this is often called the u substitution method too, because u is the common letter. So what we do is we let u be equal to that 1 plus x squared, and then we take the derivative of that. So we're going to take implicit differentiation here. So the derivative of u, we'll call it du. We're thinking of it as a function, and we're also thinking of x as a function. So the derivative of 1 is 0, but the derivative of x squared is 2x. And then by implicit differentiation, if that's a function, it's also going to be multiplied by dx. So the two things you're going to use to substitute are u and then dx. So what we want to do is we want to solve for dx. So you would do that by dividing by 2x. So we have du over 2x is equal to dx. So I'm using two parts. I'm using this u equals 1 plus x squared, and then I'm also using this du over 2x is equal to dx to change my integral. So I'm taking this integral now and I'm substituting those two things. So this will become the integral. 2x stays where it is. Then I'm replacing the 1 plus x squared with the u, because u is equal to 1 plus x squared. So this is going to be times the square root of u. And then finally the dx gets replaced by du over 2x. So our 2x's just cancel. 2x over 2x is equal to 1. And now what I'm integrating is I'm just integrating the square root of u, which is the same thing as u to the 1/2 power du. So if I do my antiderivative there, the antiderivative of u to the 1/2 power, remember I'm just adding 1 to that power, so it's going to be u to the 3 over 2, and then I'd be dividing by 3 over 2, But remember, when you divide by a fraction, it's equivalent to multiplying by its reciprocal. So I'm just going to write 2/3 in front. And then we have our plus c, since this is just a general antiderivative. And then technically what we should do is, once we've computed the antiderivative via the substitution, we convert back to the original variable. So I want to replace this u that's being raised to the 3/2 by 1 plus x squared in parentheses. So I will have 2/3 times the quantity 1 plus x squared to the 3/2 plus c. And that would be the final answer. So does anyone have any questions there? Okay, it may seem a little confusing at first, but again, you just need to get used to the procedure. And once you're used to the procedure, then things will be a little more clear, because it seems like probably a lot is going on, but we're really going to be doing the same kind of things over and over. Okay, so let's do a couple more, then I'll give you a couple to practice. So So again, we just want to compute each of these general antiderivatives. So let's say A, we're doing the integral of x cubed times 2 plus x to the 4th raised to the 5th power dx. Now again, you want to look for the things that are related, such that when you take the derivative, you get something similar to the other things. So in this case, 2 plus x to the 4th is what we want to pick to be u, because when you take the derivative, you're going to get 4x cubed, which is only differs from this x cubed by a constant. So let's see how this works. Again, we let u be this 2 plus x to the 4th. So this is one of the things we're going to use for our substitution. And then we let du be, we take the derivative of both sides, so we get du. Derivative of 2 is 0, and then the derivative of x to the 4th is 4x to the 3rd dx. And then we just want to basically solve for dx. So divide both sides by 4x cubed. So we have du over 4x cubed is equal to dx. So again, the two ingredients for changing the integral are u and this dx. Okay, so I'm going to take the integral and replace it. So I'm going to leave x cubed alone. And then the 2 plus x to the 4th, that's now being replaced by u. So this is u to the 5th power. And then dx is replaced by du over 4x cubed. So the x cubes will cancel. So then I just have the integral of u to the 5th du, which is a pretty simple integral. It's just going to be 1 over 6 times u to the 6th plus a constant. And as we did in the previous one, we can replace that u by the original substitution, 2 plus x to the 4th. So I've got 1/6 times 2 plus x to the 4th raised to the 6th power plus a constant. So that's it for part A. Let's go ahead and move on to part B.
Where did you do with the 4?
The 4, oh, I forgot all about it. So thank you. So this should be u to the 5th over 4, which would mean when you have 1 over 6 times 1 over 4, it'll be 1 over 24. So I just forgot. So that was a mistake. So yeah, 1 over 24, 1 over 24. Thank you for pointing that out. So part B, we have the integral of x squared over the square root of x cubed plus 2 dx. So again, if we let u be x cubed plus 2, the derivative is going to be 3x squared, so it's going to be similar to that. Usually with the polynomials, it's pretty easy because the substitution, you're going to pick whatever thing is higher, and then hopefully you see a polynomial that's 1 degree lower somewhere. So the substitution is usually pretty easy to identify when you've got some polynomials as the main components of your function. So again, we let u be x cubed over 2 here, and then du will be 3x squared dx, and then we want to solve for dx. So divide by 3x squared. So du over 3x squared is dx. So our two kind of ingredients for the substitution are this and this. And so our integral becomes the integral of x squared over the square root of u times du over 3x squared. So our x squareds cancel. And we've got the integral of 1 over the square root of u, 1/3 times 1 over the square root of u. So a lot of times with the constants, we can just write those in front. So I'll do that here. So 1/3 integral. And then the square root of u, we want to think of that as an exponent. So that would be u to the negative 1/2. The square root is the 1/2. And then because it's in the denominator, that's what makes it negative. So we've got u to the negative 1/2 eu. And so what you want to do is add 1 to that power. So we would have 1/3 u to the 1/2 divided by 1/2. But remember, dividing by 1/2 is the same thing as multiplying by 2. So this will actually be 2/3 u to the 1/2 plus c. And again, we want to just replace that u by x cubed plus 2. And you can even switch back to a square root if you want. So we could write this as 2/3 square root x cubed plus 2 plus a constant. And that would be our final antiderivative, general antiderivative. So are there any questions there? So let me give 2 for you guys to try, and we'll try the breakout groups, and hopefully they don't mess up again. So let me go ahead and do that. So example, we'll say try at your desks. So let's say the integral of x squared times the square root of x cubed plus 1 dx. And b, we'll do the integral of p divided by 1 plus 4p squared dp. Okay, so let me just see if I can break them into 2 groups to work on this. If I can remember how. Oh, so yeah, make sure before I do this, you guys write down the problems, because I feel like when I do the breakout sessions, sometimes the screen sharing stops working. So I think that's the one issue that happens. So yeah, go ahead and do that. Make sure you have these problems written down. So I'll give you a minute to do that, and then I'll do the breakout sessions. So again, group 1 will do a x squared x cubed plus 1, and group 2 will do p b, which is p over 1 plus 4p squared. Okay, so let me go ahead and do that. Okay, so did that. So I'm just going to do 2. Okay. Okay, so breakout sessions are over. So what I'm going to do real quick is I'm just going to jump out of the meeting and jump back in because for whatever reason, usually I can't share my screen once I do this. So let me do that real quick. So don't go anywhere. Okay, so I'm back. So hopefully I can share my screen again, and we can go over the two we just did in the group sessions there. Make sure there's no chat. Okay, good. All right, so we just did these two. So I'll go over how I would have set them up. Once you get really good at these, you can kind of just do them in your head, but for now, it's good to go through the whole process. So we want to let u for this first one be x cubed plus 1. So then du is 3x squared dx. And we divide by 3x squared. So we have du over 3x squared is dx. So again, these are the two things we're using to make the substitution. I'll probably stop circling them after a while. I just want to highlight what it is I'm actually using. So our integral becomes x squared times the square root of u times du over 3x squared. So our x squareds go away. Again, once you complete this step, your integral should only have u's. All your x's should cancel. If your x's didn't cancel out, what that means is that you made an incorrect substitution. So what we have now is just 1/3 integral u to the 1/2 du. So we have 1/3. We're going to get u to the 3/2 divided by 3/2. When you divide by 3/2, that is the same thing as multiplying by 2/3 plus a constant. So this is going to be our antiderivative. Multiplying the two fractions, we get 2 over 9. And then changing u back to x cubed plus 1, we get x cubed plus 1 to the 3/2 plus a constant. And that's it. For b, what we want to do is we want to let u be the denominator here. So 1 plus 4p squared. So du is going to be 8p dp. And then we divide by the 8p. So again, we have our two things that we're using to make the substitution. So we've now transformed our integral in from x's or from p's to u's. So we're going to get p divided by u times du over 8p. So again, the p's cancel. So we get 1/8 integral 1 over u du. And remember, the integral of 1 over u is the natural log of the absolute value of u. So this is going to be 1/8 natural log of the absolute value of u du. Excuse me. And we can switch back to the 1 plus 4p squared plus our general constant. I wrote du in the previous thing. That should be plus c. Sorry. I was just looking at the step before, I suppose. Okay, so I think people are able to get those okay. So probably we'll try 2 more, then I'll give you 2 more to work on, and that might be it for today. And then we'll look at doing substitution rules, some definite integrals next class. We'll see about the homework. I may push it back. I haven't looked and seen if it's only 5-4 as well, so I'll double check on that at the end of class here. Okay, so example. Compute. So let's look at the, we're actually going to do it now. So yeah, so we'll start with definite integrals combined with substitution. The nice thing about definite integrals is we don't actually have to substitute back. What we can do is we can change the limits via our substitution. And in doing that, we essentially can just work in U and get the final answer. So I'll show you what I mean in a second here. Now, theoretically, this doesn't need substitution, right? Because technically 3t minus 1 to the 50th, you could multiply that out, right? You could actually multiply it out and get a 51-term polynomial and then go ahead and plug in the numbers and do it just like a regular integral. But that would be very, very tiresome and boring to do by hand. So this kind of shows that the substitution rule can also help us do some integrals in a more efficient way as well. So basically for this one, what we're going to do is we're going to let u be 3t minus 1. So du is just going to be 3 dt. So 1/3 du will equal dt. So again, I'm just focusing on the substitution for u and then the solution for dt. But since it's a definite integral, we're never going to switch back to t's. We're just going to stay in the world of u's. So what we have to do is we have to switch our limits, if that makes sense. So if u is equal to 1, the top limit, then, t is equal to 1, right? Because the original limits are t values, if that makes sense. So the top and bottom of the integral, 1 and 0, those are t values. We want to figure out what the appropriate u values are. So if t is equal to 1, u would be equal to 3 times 1 minus 1. So 3 minus 1 is 2. So t equals 1 corresponds to u equals 2. And similarly, t equals 0 would correspond to 3 times 0 minus 1, which is u equals minus 1. So we can completely transform our integral both from the letters and the limits. So now our integral is going to be the integral from -1 to 2 of u to the 50th power times 1/3 du. So again, let me just write the integral on the outside, or the constant on the outside, 1/3 integral -1 to 2 u to the 50th du. And then the antiderivative will be 1/3 times u to the 51 over 51. And this is the antiderivative. It's a definite integral, so we don't need the plus c. So this is going to come out to some big number, I have a feeling. So this is essentially, let me just do one more step. I'll combine the constants. So we get u to the 51 over 153 from -1 to 2. And so this will just be 2 to the 51st power over 153 minus -1 to the 51st power over 153. And We'll see what number that is equal to. It's probably some huge number, because 2 to the 51 is pretty big. Yeah, so I'm just going to write this in scientific notation because it's so large. I don't know if I made this. Oh. No. Yeah, so I don't know. I don't know where I got this problem from, but it's some large number. We can check again in Desmos just to make sure we didn't make an error, but so I'm getting something like 1.47 times 10 to the 13th. So some huge number. Again, like I said, we can check that. So our original integral was 0 to 1 of 3t minus 1 to the 50th dt. So yeah, 1.47 times 10 to the 13th. So yeah, just a gigantic number, but we did all the steps right, so that's okay. So any questions there? I don't see any. Okay, let's go ahead and do the second one. So yeah, let's for this one. Okay, so let's say part B. Maybe we are integrating 0 to 2 of t squared times the square root of 8 minus t cubed dt. So again, 2 parts here. We want to let u be the 8 minus t cubed. So du will be minus 3t squared dt. And again, we want to divide. So du over minus 3t squared is going to be dt. So these are our limits. These are the things we use to substitute. Now we want to figure out how our limits change. So maybe I can just do that here. Save some space. So the limits, we have a t equals 2. Again, our substitution is 8 minus t squared. So if you do 8 minus 2 squared, you would get 0, 8 minus 8. So that would transform to u equals 0. And t equals 0, you would have 8 minus 0. So that would transform to u equals 8. So our integral is going to be the integral from 8 to 0 of t squared times the square root of u times du over minus 3t squared. So the t squareds cancel, which is a sign that our substitution was correct. So we have minus 1/3 times the integral from 8 to 0 of u to the 1/2 times du. Okay, so we're familiar with that. Again, the antiderivative here is going to be 2/3 u to the 3 over 2. And 2/3 times negative 1/3 is going to be minus 2 over 9. So we have minus 2 over 9 times this u to the 3 over 2 from 8 to 0. So plugging in 0, that's going to, well, we'll just go ahead and plug it in. So 0 to the 3 over 2. So this term's just going to go away. And then we have minus negative 2 over 9 times 8 to the 3 over 2. So we get 0, and then the two negatives are going to make this plus 2/9 times, so the square root of 8 is going to be 2 radical 2, so 2 radical 2 to the third would be 8 times 2 to the 3 over 2 or something like that. 8 square root 8 maybe, which is 2 square root 2. So 16 square root 2, I don't know. So 32 over 9 square root 2, I think. So that's about 5.03. Again, I'll check this one on Desmos just to make sure I didn't mess up the arithmetic at the end. So this integral was 2 t squared times 8 minus t cubed. Yeah, so didn't mess anything up. 5.03 is the final answer there. Okay, so let me check on the homework real quick. Let's see if the next assignment makes sense when the due date is. So would be this one. So let me go to the student view. Well, no, I'll just do it from here. View. So I've got this set at the 19th for right now. Does that make any sense? So we have a bunch of substitutions and then integration by parts. Yeah, so that's the next section, which is next week, parts. So yes, since this has parts, we want this due not this week, but at least next week. So probably it's going to make sense to be due something like the 12th or 15th. So that says the 19th right now. Probably it's going to be more like the 12th. So let me. This is one of our longer sections, so I don't want to rush it. So I mean, I do want to give you time to complete this assignment, but probably we're going to be moving it. So I can make it due. So if we have all of next week and then the following week, I think the 15th is maybe a better date. So why don't we make that actually do the 15th? Well, can't remember how to do this. So I want to make it do the 15th. So we have that adjustment on this one, but we'll have time to go over some of the questions. Like I said, maybe we'll do some of them this week and maybe some of them next week. While it's saving there. I don't know why it's taking so long. Yeah. Okay, so that is updated. So let's not do the February 15th. All right, so like I said, let me give you a couple of problems to try at the end of class today, and then maybe we'll start next class going over those two. So, example. So try at your desks. Well, that's what I used to say when we had class in person. I guess try at home. Maybe is better. So the integral from 0 to 1 of x squared times 1 plus 2x cubed to the 5th dx, and then b, try the integral from 1 to 3 of 4z times e to the z squared minus 1 dz. So write down both these problems, please. I'll start a breakout session, and then you can try and work on them. And whenever you feel like you're finished, you can just go ahead and leave the meeting. And that'll be it for today. And then we'll start next class by going over these two problems. So, and you can try and work on them at home if you don't get them finished before the end of class, but we'll go ahead and do it that way. So write down the problems. I'll start the breakout sessions in the recording as well. And if you have any questions, you can ask me too. So hopefully you have the problems written down. We'll go ahead and end the recording.